So in this solution, I've used M equals 501 nodes. So let's say I decided to do 101 nodes instead. This 101 nodes. So let's see what the solution looks like there. So it clearly becomes unstable. And if you can't see it, the y-axis is that number times 10 to the 65th power. So it's obviously garbage, right? And in fact, there's kind of a tipping point. I was going through and checking that before. I found it about 278. Not like I have too much time on my hands or anything. So if we look at 300, let's say, so 300 time steps, we still see that the solution kind of looks reasonable. So what does it look like when it's just starting to become unstable? So let's look at that, 278. All right, so this is what an unstable solution looks like, somewhere in that middle. And what's happening? Well, if you kind of see, you're overshooting to start, it corrects back, and then it overshoots again and corrects back, and eventually that cumulative local error gets to a point where it's going to oscillate more and more, and if we continue going out, it would become fully unstable. So then, in terms of how we actually compute that that cutoff, so let's look at this example here. So here I have, let's see, t and the ith node from the second time step to the first time step. So we're taking one time step here. In order to compute the point at which it's going to become unstable, what we need to look at is everything that's multiplying that first temperature value, right? So we have t I comma 1. Anything that's multiplying that must be positive. Right? That's the criteria. So if you think, okay, if I have something that's negative there, then this is going to become unstable. Right? You're kind of taking a negative, multiplying it by the temperature, and then adding this other stuff. So anything that's multiplying that, if it's positive, then it should be stable. So if we go through and regroup this solution, which we're doing right here, this is all we're doing is just regrouping everything to put it together on ti minus 1. You can see what's multiplying that here would be this stuff here. And so in order for this to be positive, we have to choose a time step that's equal to this, right? This is all just algebra of that term. So, how do we make sure that we would have a time step that's below that? Well, yeah, more time steps. Or we could use a different technique that has kind of more stuff that's going to end up multiplying this. Yeah. Yes, yeah, it is. And in fact, we can do, so you guys are asking really good questions. So we can go through and compare, or have a representation of how we would actually get to this based on the resistance network model. So if we look at so for this resistance network, if what we want to do is limit our delta t crit to be a stable time step, but what we're really saying is we want a time step that's lower than the time constant, right? So I think that's getting to your question. So how do we make sure it's lower than the time constant? Well, let's compute what the time constant is. So the time constant is going to be tau is equal to, so this is tau LC, right? Tau LC is equal to R to the surroundings times the specific heat of heat capacity of the object. So for this model, we actually have what? We have our surroundings is going to be our conduction. There's our conduction. There's our convection. There's another R conduction. So all those three things are resistances in parallel, right? And remember, this is for the node itself, not for the whole thing. We're just looking at one node. Okay, so if we do this, we would say tau is equal to what's our surroundings? Well, it's 1 over our conduction plus 1 over our conduction plus 1 over our convection. Right, so parallel resistance is there. And then the heat capacity of the object is going to be we'll just leave that as C for now. So let's rewrite this with our actual value. So tau becomes, let's see, this first one is K AC over delta X. Or 1 over that. So then it's 2 of those. So it becomes 2 K AC over delta X plus 1 over HA, but then the inverse of that. So that becomes H bar times the perimeter times delta X. All that to the -1. And then what's our specific heat? It's our heat capacity. It's delta X times AC. That's the volume times rho times the specific heat. Okay, so now we rearrange this a little bit. Right, so this becomes, so what we're actually going to do is divide through by this. So we're going to basically multiply both the numerator and the denominator of this thing on the right-hand side by that thing, and it ends up being the following. It ends up being tau is equal to 1 over this 2 K AC over delta X squared AC rho C plus H bar perimeter delta X over delta X AC rho C. Okay, just algebra to get there. Okay, and then the last thing is if we simplify this out, we end up with 1 over 2 times alpha over delta X squared plus H bar perimeter over AC rho times C. Okay, so just algebra to get there. So compare that with this. Right, it's exactly the same thing. So in fact, if we went through and did the lump capacitance time constant here, that is the same thing as our critical time step. So that's all we're saying is when you're taking a time step, it can't be longer than the critical or the lump capacitance time constant, otherwise it will become unstable. Okay. Any other questions? Cool. So actually we're surprisingly a little ahead of schedule. So I think what we'll talk about next time is some of the other methods, right? We just talked about Euler's today. Next time we'll get into the Heinz method or Runge-Kutta fourth order. We'll talk through those. We'll talk through the fully implicit and Crank-Nicholson method. And then we'll go through again this like the ODE 4.5 and integral methods and ease. And at this point, then you'll have a really great tool set to deal with these 1D transient problems. Okay, thanks everyone.